Welcome, this is Mrs. Roberts again with Algebra 2, and this is the third video in our Chapter 11. Now I realize that says Compound Events, Section 11.4, but this is the third video. Make sure you're watching them in the correct order. Our objective today is to find the probability of mutually exclusive and mutually inclusive events. So we need to write down a couple of vocab words. First word is a compound event. It's made up of two or more single events. For example, rolling a dice and then tossing a coin, drawing a card and then spinning a spinner. Two different things going on. Or it could even be rolling a dice and then rolling another dice. Mutually exclusive events are events that cannot both occur in the same trial and experiment. For example, like we have down here, you can draw a card from a deck, but it can't be both a face card and an ace. Those are two separate things. And so those events would be mutually exclusive. They cannot be both. When you draw a card, it can't be both a face card and an ace. It's got to be one or the other. We also have inclusive events. That's when we have what I refer to as the overlap. For example, if I draw a card that's a red, or I want to know the probability of drawing a card that's an ace, there's some overlap. There are red cards and there are aces. There are also cards that are both. So we're going to see some different examples. Okay. When you read these, they're going to be an or. What's the probability of getting a face card or an ace? What's the probability of rolling a 1 or a 7? What's the probability of getting a heads or a tails? We're talking about one draw. And what we're going to do is we're going to add the probabilities of getting each if there is no overlap. So if it's a situation where there is no overlap, like our example with a face card or an ace, there is no overlap, we would add the probability of getting a face card. Well, we consider the face cards jacks, queens, and kings. There are 3 cards in each suit, and there are 4 suits. There are a total of 12 cards, and a deck has 52 cards. Probability of getting an ace would be 4 cards because there are 4 aces in the deck, and again 52. And so then we add those together to get our total probability, which is 16 out of 52. We also have situations where there is overlap, okay, where there is some repeating. For example, the probability of getting a red or an ace. Well, you have the probability of getting reds, you have the probability of getting aces, but you have to subtract out the probability of getting both of those because I've counted all the aces here and I've counted the reds here, the 2 red aces here, and so we've counted them twice and we can't do that. So what's the probability of getting a red? Well, it's 26 out of 52 because that's how many cards there are that are red. What's the probability of getting an ace? There's 4 out of 52. But what's the probability of getting both a card that's red and an ace? Well, there are 2 of those. So we have 2 out of 52. Well, 26 plus 4 is 30, minus 2 is 28 out of 52. Now, if you were to take a deck of cards and count up all the cards that were either reds or aces, you would see that you would have 28. Okay, so let's look at some others. A group of students are donating during a blood drive. A student has a 9 in 20 probability of having type O and a 2 in 5 probability of having type A blood. So the first thing we need to ask ourselves what the question is. It says, what is the probability that a student has type O or type A blood? Right? Is there any overlap? Can you have both O and A blood? No, you can't. So these are mutually exclusive events, so we simply add the 2 events together. You have a 9 in 20 chance of being a type O. You have a 2 in 5 chance of being a type A, and so we add those. Now remember, to add fractions, we have to get a common denominator. So I'm going to multiply the top and bottom here by 4 to get a common denominator. So that's 9 20ths plus 8 20ths, or you have a 17 in 20 chance of getting a student with a type O blood or type A blood. Pretty high odds, so it's probably fairly common events. All right, you try this one. Each student cast one vote for senior class president. Of the students, 25% voted for Hunt, 20% for Klein, and 55% for Villa. If a student from the senior class is selected at random, what is the probability that the student voted for Klein or Villa? All right, you try this, pause it, and then check back to see if you got it correctly. Got it correct. All right, so let's think about that. When you vote, can you typically vote for more than one person? No, you can't. So if you vote for Klein or you vote for Villa, you cannot vote for both of them. So what's the probability that they voted for Klein? It's a 20%. What's the probability that they voted for Villa? 55%. So what's the probability that they voted for one of those? You have a 75% chance. You could have also looked at it and said, well, what percent didn't vote for either of those two? 25%. 100 minus 25% also gives me that 75%. These are mutually exclusive events. There is no overlap. Let's take a look at ones that have some overlap. This one says, find the probability on a number cube of rolling an odd number or a number greater than 2. Okay, so our odd numbers are 1, 3, 5. Right? So that's a 3 in 6 probability. Number greater than 2, that's 3, 4, 5, and 6. So there are 4 numbers greater than 2. So we're going to add those, but then we need to check, is there any overlap? Yes, 3 is counted here, and so is 5, but 3 is also counted here, and 5 is counted here. So how much overlap do we have? Well, we have 2 that are in both groups, so we need to subtract out those 2. 3 plus 4 is 7, minus 2 is 5. You have a 5 in 6 chance of getting a number, rolling a dice, and rolling an odd or a number greater than 2. Well, if you think about that, 2 is the only one that doesn't meet one of those two conditions. You have a 1 in 6 chance of getting a 2, so 5 in 6 is the remaining. And that's our answer. These are not mutually exclusive. These are inclusive. You have to remember to subtract that overlap. Okay? You try this one. A card is drawn from a deck of 52 cards. Find the probability of drawing a red card, hearts or diamonds, or a face card, jack, queen, or king. Try it. Check back with me. Let's see how you did. All right. How'd you do? Well, probability of drawing a red card. How many red cards are there? Half of the deck is red, so 26 out of 52 cards are red. Then the or says add. Face cards. How many face cards are there? Well, there's 4 of these, there's 4 of those, and there's 4 of those for a total of 12 cards. But then we have to ask ourselves, are there any of these face cards that are red? Yes, half of those face cards are red. 6 of those face cards are red, so we have to subtract that off. All right, so 26 plus 12 is 38, minus 6 is 32 out of 52. Now we can simplify that. 16 out of 26, and that simplifies again. 8 out of 13 chance. If you were to randomly draw a card from a deck, you would have an 8 in 13 chance that that card is either a red card or a face card. Remember, this is just one drawing. All right. Now, sometimes they get a little bit more complicated, and I've found that drawing a chart helps me figure it out, because then I can figure out where the overlap is. We have, of 1,560 students surveyed, 840 were seniors and 630 read a daily paper. The rest of the students were juniors. Only 215 of the paper readers were juniors. What is the probability that a student was a senior or read a daily paper? So I've created this table. Take a minute and copy that down. My J stands for my juniors, S stands for seniors, T is my total. P is people who read the paper, N is no paper reader, and T is total. This is my total. This is the total number in my group. If I look at it, they surveyed 1,560 students. That's got to go there. 840 were seniors. All right, so 840 of my total were seniors. That's this number here. It doesn't say they were paper readers who were seniors, or non-paper readers who were seniors, they said 840 of those were seniors. And 630 read a daily paper. So 630 of our total read the daily paper. Only 215 of the paper readers were juniors, so that number is going to go right there, 215. But how do we figure out the rest of these categories? Well, think about it. If we have a total of 630 paper readers and 215 of them are juniors, how many had to be seniors? Right, 415. If there are a total of 840 seniors and there are a total of 1,560 students, then how many of those would be juniors? You take the 1,560 minus the 840, and you would get 720 of those would be juniors. Now, you've got this whole row here. How do we figure out how many go here? Well, we can do it a couple of different ways. How about we look at this column right here? 415 plus some number has to be 840. Well, what does that have to be? It's got to be 425. 215 plus some number has to be 720. That's got to be 505. 630 plus some number has to be 1560. And so then this number can be found by doing either way. We can take 1560 minus 630, that's 930. Or we could say 505 plus 425, that's also 930. Now that we've got the chart filled in, we want to know what is the probability that a student was a senior or read a daily paper. What I like to do is and I'm going to change my color here so we can see. I like to circle the two columns that I'm talking about. I want to know how many either read a paper or were a senior. And this helps me out greatly. All right, how many read a paper? 630 out of 1,560 read a paper. How many were seniors? Total, remember, we're looking at. So we're going to add the number of seniors, 840. Out of 1,560. But is there any overlap? Are there any seniors who also read a paper that we've counted twice? These 415 have been counted twice. They've been counted in this row and they've been counted in this column, so we have to subtract them off. We can't count them twice. All right. Remember, when we add or subtract fractions, we do not change the denominator. So let's look at our numerator. 630 plus 840 is 1,470. 1,470 minus 415 would be 1,000. And 70 minus 15, I believe, is 55. 1,055. That's the probability. Now, if we wanted to, what we could do is we could divide that out. We could say 1055 divided by 1560, and that's 0.676. Because remember, probabilities could be expressed as a decimal. So it's a 0.68 or 68% chance that if you randomly choose somebody that they read the paper or are a senior. If you would like to practice another one, here's another one that you can practice. If not, you can go ahead and do the summary. I'll come back and do this practice one here in just a minute. Here's the summary, or here's to prepare for tomorrow. Summarize what you learned and write at least one question you have about the lesson. Would you like more practice? Let's try this one together then too, or try this one and see what you think. Can you do these? Notice the or. Smoker and married, that's a tricky one. We have 350 people, 200 are married, and 50 are single. All right, so we have 250 people, 200 are married, 50 are single. These are talking about our totals. So how many are divorced? The rest, it says, are divorced. Well, oops, that should be a 350. That's what I did wrong. So how many are divorced out of our 350? Out of our 250? Yes, 350 is the number I'm looking for. So let's erase that. And go back to our pen. So 200 were married, 50 were single, 350 was our total, so that leaves 100 to be divorced. Okay? 54 of those married smoke. So we have 54 married smokers. You have to be careful how you interpret that. 39 of those who are single are non-smokers, so that's this number here, the 39. There are 38 divorced smokers, so the 38 goes here. So then we can figure these out. 50 minus 39, that should be 11. 100 minus 38 would be 62. And 54 minus 200 would be 146. Then we can add across to find these two totals. 54 plus 11 is 65. 65 plus 38 is 103. Now we could do work backwards here. This should be 247. And double check. Does 146 plus 39 plus 62 equal 247? I think it should. All right, so what's the probability that there's a smoker or that they're divorced? Okay, so here's the smokers. Here's the divorced. Probability that they're a smoker, 103 out of 350. Divorced, 100 out of 350. The overlap, that's this one right here, 38 out of 350. So we have 203 minus 38. Just going to double check that because my math in my head sometimes doesn't work like it should. That'd be 165 out of 350. If you wanted to figure that as a percent, take 165 and divide it by 350. And so you have a 47% chance of choosing somebody that was a smoker or divorced. What about divorced or single? Well, let's think about that. Okay, so we don't need this column anymore. We need the divorced or the single columns. All right, so we've got the divorce circled already, and then we've got the singles. So the probability that they're divorced is a 1 in 350. This or, remember, says add, so we're going to add to it the probability that they're single, 50 out of 350. Is there any overlap? No, because you can't be both single and divorced, so there's nothing to subtract. These are mutually exclusive events. So we have a 150 out of 350 chance of choosing somebody that is divorced or single. How about a smoker and married? Well, how many of those are smokers and married? Right, just those 54 right there. Out of the total, there is nothing else to add it to because there's not two conditions. We've got them all right there in that column. All right, if you have not yet done your summary and your question, please take care of that now, and I'll see you tomorrow. Bye.